Hello and welcome, everyone. I am absolutely thrilled you're joining us for this explainer. If you've ever stared at a really complex math problem and wondered, how does this actually relate to real life? Well, you are in the exact right place. Today, we're diving into a genuinely fascinating topic, understanding numbers. I want you to think of numbers as the ultimate toolkit we use to describe, measure, and navigate the physical world around us. We literally use them all the time, whether we're buying a cup of coffee, checking the weather, or figuring out how far away something is. But really, how often do we stop and actually look at the numbers themselves?
It seems incredibly straightforward when we're counting physical, tangible things, right? But I want you to ponder a simple yet profoundly mind-bending question. How do we count what isn't there? How on earth do we mathematically represent absolutely nothing? Or, even stranger, less than nothing? This exact question puzzled ancient scholars for centuries, and it sets up an incredible mathematical mystery that eventually led to the invention of zero and negative numbers. So, to solve this mystery, we're going to look at the logical evolution of numbers. We'll start with counting the real world, move on to the magic of zero, explore going below zero, take a look at zero, the neutral core, and finally map out the number family tree. All right, let's kick things off with section 1, counting the real world, natural numbers.
Okay, let's dive into this mathematical journey with what we call natural numbers, which are represented by the letter n. By definition, this is the infinite set of positive, whole numbers used for basic counting. And the key here, they start exactly at 1. Let's use a simple analogy. Think of looking into a basket of apples. If there's an apple in the basket, you say 1. If there's another, you say 2. You never start counting the apples at 0, right? And you wouldn't count a whole apple as 3.5 or a half. Natural numbers are always positive. They always start at 1, and they strictly do not contain fractions or decimals of any kind.
So, the really crucial takeaway is that natural numbers are incredibly grounded in our everyday physical environment. We use them for tangible things all the time. Counting objects, like, say, 6 students in a room or 10 pencils on a desk. We use them for arranging items in order, first, second, third. We use them for everyday labels, like classroom 4, and for comparing quantities to see who has more. They are, quite literally, the most basic building blocks of mathematics. And the crazy thing about natural numbers is they never, ever end. That's because of a really simple rule. Every single number has a successor. Just pick any natural number. Let's say 4. Simply add exactly 1, and boom, you arrive at the next unique number, which is 5. No matter how massively huge a number gets, a million, a billion, a trillion, you can always just add 1 to get the next one in line.
Moving right along to section 2, the magic of zero, whole numbers.
But here is where we hit our very first mathematical wall. Remember our basket of apples from earlier? Well, what happens if you get really hungry and you just eat all of them? You reach into the basket and, well, there's nothing left. How do you write down nothing using natural numbers? You actually can't, because, as we established, natural numbers start at 1. So while natural numbers start at 1, we had to invent a brand new set, the whole numbers, which starts at 0. And that single, totally crucial difference, it changed mathematics forever. To really anchor this concept, we define whole numbers, represented by the letter W, as a set of non-negative numbers that includes all the natural numbers plus 0. And remember, they still don't have any fractions or decimals. Essentially, you can think of the whole number set as just the natural number set holding hands with 0. It's that simple. With this new set, you can easily represent 0 candies, 1 candy, 2 candies, and so on. It handles addition and multiplication absolutely perfectly. But wait a minute, we just hit another uh-oh moment. Whole numbers are great, for sure, but they still have limits. What happens if we try to subtract a larger number from a smaller one? If you only have $3 in your pocket and you try to spend $7, what happens? If we literally write out 3 minus 7, we completely break the rules of whole numbers, because whole numbers cannot go below 0. Which brings us to section 3, going below 0, integers. This exact subtraction problem forced us to expand our toolkit once again. To solve it, mathematicians formalized integers, represented by the symbol z. An integer is basically an infinite set extending in both directions. It includes all our positive whole numbers, our 0, and here is the really cool new part, their negative opposites. So every positive integer now has a mirror image. The exact opposite of 5 is negative 5. The opposite of 8 is negative 8. Picture a horizontal timeline, or a number line, in your head. Right smack in the middle, you have your neutral 0.
If you move to the right, you're counting up into the positive integers, 1, 2, and so on. But now you can also move to the left. You can go backwards from 0 into the negative integers, -1, -2. We finally have a mathematical way to travel in two completely opposite directions.
And I want to stress that negative numbers aren't just some abstract idea made up by math teachers. They are absolutely essential tools we use daily. Think about the temperature dropping below freezing, or think about your bank balance showing a profit as a positive and a debt as a negative. Think about getting in an elevator and going down past the ground floor into a basement parking garage. That is literally negative space. Mountain heights above sea level are positive, while the depths of the ocean are negative. Integers allow us to measure all of these real-world contrasts perfectly. All right, let's jump to section 4, 0, the neutral core, and the additive identity. Now, before we bring this whole family tree together, 0 really deserves its own dramatic spotlight. It is the critical anchor for all the number sets we've talked about so far. Think about it. Positive numbers are greater than 0, and negative numbers are less than 0. Therefore, 0 itself is the only integer that is neither positive nor negative. It sits perfectly balanced right in the middle of everything. Because of this totally unique status, 0 is known as the additive identity. 5 plus 0 is just 5. 100 plus 0 is 100. -7 plus 0 is still -7. Adding 0 to any number does not change its value whatsoever. It is the ultimate neutral player in the game of mathematics, allowing operations to happen without altering the original quantity. Finally, section 5, the number family tree. Let's test these operations. So let's step back and see how this all builds together. Our mathematical journey has acted sort of like a set of Russian nesting dolls. Let's walk through some basic operations. Addition, like 6 plus 2, works beautifully across all three sets, natural, whole, and integer. But subtraction, like 3 minus 7, well, that breaks the natural numbers. It breaks the whole numbers. It only works once we invent the integers. Now look at division. What happens if we try to divide 8 by 3? Well, this brings us to one universal, non-negotiable rule shared by the natural, whole, and integer sets. Absolutely none of these foundational number sets can handle fractions or decimal points. Whether it's 2.5 or 2.67, these three sets are strictly about whole, complete units. They are amazing tools for counting apples, marking basement floors, and balancing checkbooks, but they completely fall apart the exact moment you try to split something into pieces. Which leaves us on an incredible cliffhanger. Mathematics, as you can see, is just a constant evolution of problem solving. We invented whole numbers to explain an empty basket. We invented integers to explain debt and going below 0. So I'm going to leave you with this provocative question. If integers absolutely cannot divide 8 by 3 cleanly, what entirely new universe of numbers do we need to invent next to handle all the fractions and decimals of the real world? Thank you so much for joining me in this explainer. Keep wondering, keep questioning, and I will see you next time.